up, housekeeping things. Um, remember to at least once a week. Well, probably more than that, but make sure that you're logging into Moodle and keep getting familiar with doing that. As far as the learning goals and objectives that I put for each chapter, go through there. If you go on the individual chapter in Moodle, you can see the same things that I'm posting. All of that. I am planning on having a quiz on Friday that's going to cover mostly chapters 1 and 2, what we've covered the past 2 weeks. I will include a little bit of chapter 3 as we're going through it, but nothing that we cover beyond Wednesday, because Thursday and Friday stuff, the quiz is going to be on Friday, but Thursday stuff, I don't want to throw that in there when you just got it the day before. So I am going to try to have that. Make sure if you haven't finished chapter 2, make sure that you're working on the chapter 2 active problems for like y'all that were out. I'm going to extend the date if I need to. I'll look at each person individually that was out on that. So just make sure that you're covering that material and all of that. It's due tonight. Like I had it set for tonight, I think at like 11:40 something p.m. But just know that stuff's happening. I've already opened up chapter 3. Now what you're going to find is the most of the stuff on chapter 3 should be fairly easy. It's mostly going to be definition stuff. There's a little bit of math towards the end. The math that we have for it is converting Celsius to Fahrenheit, Fahrenheit to Celsius, and then like converting Celsius to Kelvin. And then there's one other formula that we're going to get, and it's called specific heat. It's a formula that you just plug in the numbers and multiply or divide. It's not one that's using dimensional analysis like we've been doing. It's more just plug and chug type equation. So for chapter 3, what we're going to start looking at in the area that we're going to focus on today is being able to differentiate between an element and a compound, differentiate physical property from chemical property. So we're going to be looking at matter in terms of physical characteristics versus chemical characteristics, giving a fuller definition of matter than we did in chapter 1. And then while we're doing that, also be able to look at law of conservation of mass, do some really simple basic calculations of that. We already covered a little bit of it in chapter 1 as well. So this is going to cycle some of those things that we did in chapter 1 as well. Looking at solid, liquid, gas, just kind of overall properties of them. And then also look at chemical and physical change versus properties. And then be able to take, we're going to look at a characteristic of matter that we identify it as a pure substance or a mixture. And see how they fall into each of those categories. So today, the only math that we will have today is simple addition, subtraction, and it's just going to be looking at a total mass on the left side of a reaction versus the right side. All right, so recall from chapter 1, we defined matter as anything that occupies space and has mass. So volume, and then mass, it must have material in it that we can measure. So, and that's a definition we've already gotten, but again, it's not going to go away anytime soon. So we're going to break down matter a couple of different ways. So we can talk about, the first thing that we're going to talk about is the states of matter, all right, or the phases of matter. So in chemistry, we only care about three phases, or three phases of matter, three states of matter. So instead of states, we can also say phases. So I know that there are a couple of other phases of matter that you probably heard of. You probably in elementary, middle school, you might have talked about plasma. All right. In chemistry, as far as chemistry is concerned, all plasma is a excited gas. All right. Plasma is still looked at like a gas. And then there is also there's a state of matter that really it only matters in certain areas of physics that's below a solid, where when you get things to a low enough temperature, and this has to do with like semiconductors and things like that, that where you get it cold enough, the atoms actually start moving like a wave again. So it's kind of a very unique, specialized area of physics that chemistry doesn't care as much about either. So chemistry, we're going to worry about solid, liquid, and gas. Remember that everything that exists as matter can be in a solid phase, a liquid phase, or a gas phase. All right. So that's kind of the big thing there. Now we're going to go into what I'd like for you to do. I'd like for you to create a table on your page with 6 columns and 4 rows. And I'll pull it up so that you can kind of, so you're going to have one column that says state, second column that says molecular motion, molecular spacing, shape, volume, and compressibility. And then for the rows, solid, liquid, gas. And we'll talk about these individually. Hopefully there's nothing new that you're not. The only thing that you might be getting a little bit of new info here is you might not have used the word compressibility in terms of solid, liquid, gas before. Everything else you should have talked about when you've looked at these before in the past. Give me a minute. All right. So when we think about an object as a solid, when we're talking about the atoms in a solid, remember that a solid object, the shape is fixed, the volume is fixed. So it's not going to change size or shape unless we force it to. So when we talk about the atoms, if I'm looking at it at a solid at the atomic level, we have these atoms that are going to make a solid shape, and I drew it as kind of a box for that structure. It's going to hold its shape, and then There is a little bit of space in between each atom, but not a lot. So the space allows those atoms to vibrate back and forth just a little bit. And so that leads to, like, every solid matter, every piece of solid has what's called a resonant frequency. And it's the frequency at which those atoms vibrate back and forth. They don't vibrate enough that they fall apart, but they vibrate just enough that they maintain their shape, and they do have a little bit of energy. All right. As you heat up that solid, it gets more and more energy, and then eventually it's going to go to a different state. But that's going to be where that. Now, again, in the looking at it at the atomic level, those atoms are real close together as well. So the atoms will vibrate in a fixed position. They're close together. So that means the shape, it's going to maintain its shape. So this stapler, if we were to set this stapler on this desk, close this room up, leave it for a year, come back again and look at the stapler a year from now, the stapler is going to look exactly like it does. It might have some dirt on it, things like that, but the shape of it's not going to change. All right. If I take a hammer to it, the shape will change. All right. But so we can force a shape change, but it doesn't change on its own. The volume is going to have the same amount of, it's going to take up the same amount of space. Now, in terms of being able to compress it, in general, a solid is considered to be incompressible, meaning you can't squish it down any. Now, think about when you think about objects like a super bounce ball or something like that. Rubber does have some compressibility. That compressibility actually has to do with air spaces in between the molecules. So you're not compressing the molecules themselves, you're compressing gaps in between. So like cork has a lot of different holes in it and all of that. So the compressibility of that is that. But when you're talking about this desk, if I took a piece of this desk and I put it under one of those, I know y'all have seen the videos where they show that hydraulic ram just pushing down on it. When you have something that's a true solid, it just shatters because it can't compress. But if you have something that has air spaces in it, then it's going to go down. So when we talk about compressibility, we cannot compress a solid. All right, so liquids start changing a little bit. So in terms of liquids, we have to look at liquid inside of a container. And so the atoms get a little bit further apart. So the atoms are kind of free to move relative to each other. So those atoms can move within each other and kind of flow. I actually kind of like to draw them more like a string of like Mardi Gras beads, so that they're connected, but they're not rigidly connected like a solid. The molecules are still close together, but they're not so close that they can only vibrate. They can move. They can flow and all of that within each other. So if you think about a crawfish pot that you boil crawfish in, when you just pour the water in there, there's not a lot of motion to it. But once you turn the burner on, when you add that heat, you can start seeing that rolling boil. But the volume of the water doesn't really change. You just see the water molecules moving around. All right, that's kind of what I'm talking about, that they can move without that change. So we consider the shape indefinite because you might have heard it phrased like this. It takes shape of container. All right. So it takes the shape of the container. If I poured the water that's in that pot right there into a flask, it's going to change the shape to the flask. All right. If I turn it on its side, it's going to rearrange to fill up what it has. So the shape is indefinite, but the volume, it maintains the volume. If I pour out 500 milliliters of water, it's going to maintain 500 milliliters of water. And then, and again, in general, liquids are incompressible as well. So when you start looking at the properties of like hydraulics, the whole thing that makes hydraulics works is the fact that if you push on a liquid here, it's going to push somewhere else. So the fact that liquids don't compress allows us to manipulate it and put a small force here and create a larger force over here spread out over an area. So again, liquids are incompressible. And then the last one, gas. If we're looking at a gas in terms of in a container, gases are going to fill the whole container. All right. So gases are free to move relative to one another, just like a liquid. But the molecules are really, really far apart. The shape is indefinite because it expands to fill the container. And then the volume is indefinite because gases are compressible. So because I can keep forcing more gas into that container, the gases can be compressed. If you think about like the tires on your car, all right, they have, if you read the side of it, it says a recommended inflation pressure, all right, but we can fill it more than that pressure. We can fill it less than that pressure, and that's just meaning that we're adding more we're adding more gas molecules or removing gas molecules from it. So the fact that gases are compressible makes both the shape and volume indefinite, meaning the shape and volume can change. I can have the same number of molecules of a gas, but increase the pressure and make it a smaller area. And so taking advantage of that property of a gas is how we get pneumatics. Being able to move pistons and things like that with air. It's not on here, but if I were to add one more column, and call it energy. In terms of energy, which set of molecules would have the highest energy? Gas. So gas is going to have high energy. Which one's going to have the lowest energy? Solid. So liquid is somewhere in between. It's kind of got medium energy. All right. So that's one way that we can look at matter. We can look at matter in terms of its physical state, solid, liquid, or gas. Another way that we can look at matter, and I'm going to put the whole chart up, but I'm going to go down one side first. So another way that we can look at matter is we can consider it either a pure substance or a mixture. All right. If it is a pure substance, it will either be classified as an element or a compound. Elements can be found on periodic table of elements. So if it's an element, it's going to be one of these 118 things on here. All right. Key thing about elements. So the example they're showing is a piece of copper. All right. So they're showing copper right here. No matter how small I make that piece of copper, it's still copper. So you cannot break down an element. Once it gets to an atom, you can't break it down anymore and it still be what it is. If I break down an atom, then it makes other substances. So one of the things that we take advantage of, the way that we produce like nuclear power and all of that, or we actually gather energy from that to create steam. Nuclear power is actually a big steam generator. But we'll take like uranium-235 and we'll split it. When we split uranium-235, it produces thorium, and I forget what the other byproduct of it is. But it'll create two smaller atoms that are two different things from the original atom. So we cannot break down an element or an atom and maintain the properties of that atom. Compounds, on the other hand, compounds contain two or more different elements. So a compound, this case, this is sugar, sucrose. But I'm going to use a little bit easier one. The thing about compounds is we can write them as chemical formulas. So we can have things like NaCl. We can have things like glucose that you're familiar with, C6H12O6. We can have carbon dioxide. We can have water. But notice how we have to show a relationship from one atom to the other. Those proportions are fixed. So for water, it has to always be 2 hydrogens to 1 oxygen. For glucose, it has to be 6 carbons to 12 hydrogens to 6 oxygens. If we remove an oxygen or add something else, it changes what it is. So compounds contain 2 or more elements, but they're in fixed proportions. The mixture is always, or the ratio is always the same for each compound. We can chemically separate these elements. We can chemically separate these back into elements, but we can't physically separate them. I can't take a salt molecule with my hands and pull it apart. I have to use a chemical process. That chemical process is going to be through an electrical, some sort of electrical reaction. All right. And so elements and compounds are the only things that are considered to be pure. I will warn you on this that from time to time in questions, the book or the test will say, instead of saying pure substances, it'll just say substances. All right. But when you say a substance, you're assuming an element or a compound. Now, coming over here to mixtures, we have 2 types of mixtures. We can either have a homogeneous mixture or a heterogeneous. Now, let's see what your biology memory is. The prefix homo, it means same. All right. So when we look at a homogeneous mixture, that means when we look at it, it's going to look the same throughout. You're only going to see one type of particle, and it all looks the same. So think things like sports drinks, like Gatorade or Powerade or something like that. We have this is hot tea, but sports drinks, Kool-Aid, tea, coffee, anything when you just have what that is. Salt water is kind of funny on this one. If we're talking about salt water that we prepare in the kitchen or in the lab, that's going to be a homogeneous mixture. But if you're talking about salt water is in terms of you go to the beach and you take a cup and you scoop it up, that one's going to end up being heterogeneous because when you take it out of like an ocean or a lake, it's going to have other things in it, like maybe fish, dirt, things like that as well. So homogeneous, it looks the same throughout. The particles are evenly distributed, essentially. Talk about this later, but this blue solution is considered to be a homogeneous solution. All right. The blue part of it, if I shake it up, there's some dirt on the bottom that's in there. But if I let it settle, the blue part is homogeneous. All right. Heterogeneous. And so again, the prefix from biology, hetero, means what? Different or unlike. So heterogeneous, we're going to see different types of particles in the mixture. The example I like to give for it is when you look at a pizza, can you see the different components that make up the pizza? You can see the cheese, you can see the sauce, you can see the meats or vegetables or whatever. You can see the crust, you can see the grease, you can see all of those things in it. So heterogeneous means that it's a mixture of things that can separate or that we can see separate particles. All right. So in this case, this is a mixture of oil and water. If we let oil and water sit, it's going to separate into layers. All right. There are some types of heterogeneous mixtures that won't settle out or won't separate, but you can still see the different particles. The ones I like to think of, if you ever had that hand soap that has the little beads in it that you can wash with, when you look at it, you can see the hand sanitizer or the hand soap, and then you can also see the little micro beads in it. That's one that it never settles, but you can see the different parts. All right. So the next few slides, I'm just going to give you like a written definition of a couple of these. Take them down as you need to, but don't feel like you have to write every word of it. All right. So let's start with pure substance. So a pure substance is composed of only one type of atom or molecule. So remember, it can be an element or a compound. A mixture is composed of two or more different types of atoms or molecules. So when we talk about pure substance, again, I'm going to talk about maybe copper, gold, silver, water, carbon dioxide. All of those are representative of pure substance. When we talk about mixtures, you might have things like mud, air. Pizza. All right. Granite. All right. So I'm going to list those three at the bottom. So things like bronze, brass, and steel are a special type of mixture. They're metals that are made of mixtures of different metallic elements. they're all considered to be alloys. So bronze and brass, they're made up of varying compounds of things like copper, nickel, and tin, and some other elements here and there in smaller amounts. Steel is mostly going to be iron and carbon, and it's going to be refined iron with carbon exposure and things like that. So those, when you look at a piece of brass, you can't see where the copper starts and the nickel ends. So all of these alloys are always going to be homogeneous. All right. So alloys will always be homogeneous. Another alloy that you might be familiar with if you've ever had metal fillings in your mouth for your teeth, those are a silver, used to be silver mercury amalgam. They quit using mercury. I think they use gallium now because gallium is not as toxic as mercury. But it is an alloy of two metals, or sometimes they're gold and mercury, things like that. All right. So, definition of an element. Element is a pure substance that cannot be broken down into simpler substances. So, key thing about an element is you can't chemically break it down or physically break it down and it maintain what it is. I will tell you, I'll talk about that in a different point. A compound is a pure substance composed of two or more elements fixed in definite proportions. So again, when we talk about a compound, it means it can have that chemical formula. Salt is always going to be NaCl. Glucose is always C6H12O6. Ammonia is always NH3. So, in those relationships like that, water is always H2O. So compounds are more common than pure elements because a lot of elements won't exist alone in nature. All right, they have to be combined to something. But we can decompose compounds into simpler substances, but we have to use a chemical process. All right. So we can break compounds down, but we can't separate them. Now, so all right. So there are 7 elements off the periodic table: oxygen, fluorine, hydrogen, nitrogen, chlorine, iodine, and bromine. they are what's called diatomic elements. So, our diatomic atoms. So these 7 are considered to be diatomic. Now, in nature, when we look at oxygen, most of the time when we look at oxygen, it's going to be O2. Sometimes oxygen is even O3, ozone. But most of the time when we find oxygen, it's O2. Fluorine is a diatomic F2. Hydrogen, H2. Nitrogen, N2. Chlorine, Cl2. Iodine, I2. And bromine, Br2. Even though they are technically... So we can call these molecules, but they are not compounds. So looking at those, why would we be able to consider them a molecule but not a compound? So one of the kind of key things that distinguishes a compound just from 2 atoms combined, like in this case, compound is going to be 2 different atoms. So when we use the term compound, we're looking at least 2 different atoms. But a molecule, so like oxygen looks like that, or we visualize oxygen as one oxygen atom double bonded to another oxygen atom. But it's not a compound because the only thing there is oxygen. So we can still consider it an element. We can consider it a molecule. We can consider it an element, but it's not a compound. That's a question that they pull out. So that's something I know they ask. So just kind of be aware of that. All right. So, a lot of compounds can be molecules, but not all molecules are compounds. I can say it like that. So, O2, F2, H2, all of those can be considered molecules, but they can't be considered a compound. This can be considered a molecule. This can be considered a molecule. This is considered a formula unit because it's ionic, but we'll get more into that later. I just really want you to know these 7. They can be called molecules and elements, but they cannot be called a compound. So just those 7. And the rest we'll get later on in the course.
Wait, so what's the difference between a compound and an element?
Compound.
A compound and a molecule.
Well, let me say it like this. All compounds can be molecules, but not all molecules are compounds.
Why?
What do we have in this? What's the only thing that exists in this molecule? Fluorine. All right. So F. All right. But this is a molecule as well. But what do we see in there? We see carbon, hydrogen, and oxygen.
So molecule is only one, compound is all of them.
A compound, to be considered a compound, it has to have more than one type of element. 1, 2, 3, 1, 2, 1, 2. All right, that makes it a compound when it has different types of atoms in it. This is a molecule and a compound. This is a molecule, but not a compound. So if it only has one type of element, it's not a compound, even if it has more than one atom of that element. I'm trying to find a better way to say it, but that's the only way I can think to say it. So in that,
7 are molecules and not compounds.
exactly.
That's all.
All right. Moving on, the 2 different types of mixtures. Homogeneous mixture. A homogeneous mixture looks the same throughout. So the example that we're going to give you is like sugar, like sweet tea. You can't see the sugar or the tea. You just know it's there. All right. Heterogeneous mixture, different particles and substances can be seen. The example that I'll give you there is pizza.
Anybody have a Chrome charger? Yeah, I need one too.
All right. So all three of these boxes represent mixtures at an atomic level. All right. So looking at these three boxes, can you tell me one that might, just based off the definition, and don't be afraid to get this one wrong because we're going to talk about it. Looking at these boxes, do you see one that would represent, if we're looking at it from a backed off position at the macro level, a real world level, which one of these would represent something that's homogeneous? All right. So this one is definitely homogeneous because it's a predictable pattern, so they're spread out equally. All right.
The second one could be it too.
Okay. That's what I was about to say. I would consider the second one homogeneous as well because
It's a pattern.
there's an equal number of each type of particle. All right. What if this one? I'm going to tell you this one is heterogeneous, but if we were looking at it, if we were looking at this in a glass or something like that, what would you see when you looked at this? All right, three kind of layers or three rows. All right, so think about like if you've ever seen a density column or something like that, where they have oil, water, and then maybe something else in there. So these they have separated, so it's heterogeneous because we have different types of compounds in there. So it's a mixture. This one is a mixture of compounds. This one is a mixture of compounds. I would consider this one a mixture of elements or a mixture of atoms. All right.
Because they're the same.
Well, so here you see the open circle, the closed circle are attached to each other. So that's a compound or a drawing of a compound. Whereas this one, each one is separate, but they're near each other. They're not connected to each other. So those are going to be elements. So, homo. hetero. All right. All right. So let's look at a question. All right. So classify each type of matter as a pure substance or a mixture. If it's a pure substance, I want you to classify it as an element or a compound. If it's a mixture, classify it as homogeneous or heterogeneous based off what you know. So a lead weight. All right. It's pure. So that means lead. So they use the term lead. So that means that it's going to be the element symbol Pb off the periodic table. All right. Now, so lead is only Pb. So this one's going to be considered to be an element. All right. What about seawater? That is a mixture. All right, mixture. Now, I heard different people say homo, somebody said hetero. Think of it this way. If I go to the Gulf of Mexico and I grab a bucket of water from the Gulf of Mexico, that's seawater. Is it going to have just the salt water in it, or is it going to have other stuff in it? It's going to have stuff in it. So, and if we let it sit for a little while, the dirt and stuff will settle out. Anything that floats will float to the top, and then we'll have those layers. All right. What about distilled water?
It's a mixture and it's solo.
All right, distilled water. So think about water. We can write water as, so it is it a mixture or is it pure?
Mixture.
Pure.
How? It has two elements that are different.
So there's two things that can be considered pure: elements and compounds. So it's pure and it's a
So I said
compound.
right?
Water is always going to be two hydrogens and an oxygen. If it's anything else, it's not water. All right. So water has a definite composition. It has two hydrogens, one oxygen, so it's a compound, so it's considered to be pure. Don't think pure like nothing else in it. Think pure that it can only be that thing. All right. So you can have pure sugar, but that pure sugar is a compound of carbon, hydrogen, and oxygen.
So pure is the only thing that can be.
That's the only thing it can be. When it's in that arrangement, that's what it is. Because I can have another compound that contains hydrogen and oxygen.
But it can split apart basically.
I can have this one, you drink it, and you're fine. This one, you drink it, you'll get sick or you'll die. All right. So water, if I add another oxygen to it, it becomes hydrogen peroxide. While it's great for cleaning your teeth, it's not so great for drinking. It's great for cleaning cuts, but it's not so great to drink. You've never used hydrogen peroxide on a cut?
Not in my teeth.
Yeah, every time you look on the back of your ingredients of your toothpaste, I can guarantee most of them have hydrogen peroxide in it. That's what causes it to bubble when you brush. That's why you're supposed to spit it out and not swallow it. Don't swallow toothpaste. All right. Italian salad dressing. So think like, so if
It's a mixture and it's hetero.
mixture hetero. All right. So think about, so Italian dressing, correct me if I'm wrong. Italian dressing's the one that has like the little pepper kernels in it. And it's got oil and vinegar in it. All right, you let it sit. The pepper kernels settle to one place. The oil and vinegar is going to separate, and all of that. You have to shake it up each time. I don't eat salad, so I'm not real familiar with dressing. Or I don't use dressing even if I do, because like I'll eat raw spinach, but I don't. But I don't eat the stuff on top of it. All right. So again, another visual checkpoint. So how would you classify circle A?
It's a mixture, but it's homeo.
Is it a mixture? What do you notice about every one of these particles?
They're the same.
They're exactly the same. So if the black ones represent oxygen and the white one represents carbon, this is CO2. All right. So I have carbon dioxide, carbon dioxide, carbon dioxide, carbon dioxide, carbon dioxide. So this is a pure substance and its compounds. All right.
The next one would be a mixture and it's hetero.
All right. So this one is a mixture, but
Homeo because it's the same.
if I draw a line of symmetry, is this part of it going to look the same as that part of it? I mean, if you think of it in a much larger scale, like a glass, it'd be like Gatorade. You might have a little bit more sugar in one part than the other, but it's relatively the same appearance. So I would probably call this one homo. All right. It's hard to tell sometimes at this level. We could draw that line and count how many black dots, how many white dots. If there's more black dots on one side than the other side, then we might call it hetero. All right. Same thing here. Is this a mixture or pure? I have two different types.
A compound, so it's a mixture.
So it's a mixture. All right. Hetero to homo, I would.
If it's the same compound, it's pure. If it's two different compounds, it's a mixture. I'm understanding.
Yeah. All right. This one, I might call it more of a hetero, just because it looks like it's kind of unbalanced. There's more black molecules over here, more white molecules over here. That one's kind of hard to say. At this level, hetero and homo is kind of hard to distinguish, but we can definitely distinguish whether it's a pure substance, a mixture, or not. So this one, would it be a mixture of elements or compounds? Elements. And then this one be a mixture of compounds. All right. All right. So we're going to real quickly distinguish between properties and changes. So a physical property is a property that a substance displays without changing its composition. So what is one physical property of your desk?
It's hard.
Okay, it's hard. What's another physical property of our?
Brown.
Give somebody else a chance. What's a physical? What's a physical property of the chair you're sitting in? Okay, red. Some of them red. Some of them are blue. Things like that. So physical properties are going to be things like color, texture, hardness. You can also get into the phase of matter. Is it a solid, liquid, or gas? Physical properties, we can take technically, in some ways, a measure of the temperature of that object could be a physical property because we can take the temperature of it without changing it. We can take the mass of it. We can take the volume of it. We can take the density of it. All of those things we can do without changing it. A chemical property is one that a substance displays through changing it. So, a chemical property of our desk may be that it's flammable. But the only way that I can demonstrate that property of it is by setting it on fire and proving that it burns. All right. Another chemical property of, so flammability, corrosiveness, reactivity, all of those kind of things are chemical. How does it interact with other things around it? So physical property, we can look at it without changing its composition. Chemical property, we have to change its composition. Does it react? All right. So there's a group of elements on our periodic table all the way to the far right side. If you're looking at the one on the wall, we have helium, neon, argon, krypton, xenon, radon. All of those have one chemical property in common. Does anybody know the name for the group, that group of elements? What it's called?
What group?
The ones in red on the right-hand side of the periodic table.
They are called chemicals.
Good try. They are called the noble gases. Does anybody know of a specific chemical property of noble gases? Yeah. So they have a full outermost ring, and since that outermost electron ring is full, what else does that make them not want to do? They don't want to react. So every one of those elements are considered to be, I'm going to use the science word, which is inert, but inert means non-reactive. All right. Now, go on the opposite side of the periodic table, and I'm going to exclude hydrogen from it, but lithium, sodium, potassium, rubidium, cesium, and francium.
They're both inert.
So, noble gases are the least reactive on the periodic table. Those over there on the other side, those are called the, if I can spell it right, A-L-K-A-L-I, alkali. They're called the alkali metals. And does anybody know what happens if I take a hunk of sodium and drop it in water?
It'll burn up.
It's very reactive.
It's very reactive with water. So all of those elements are highly, highly reactive. So these are reactive. So the word inert means non-reactive. There's not really a word for super reactive, but those are super reactive. In fact, the further you get down the list, the more reactive it is. So if I take a hunk of sodium and I throw it in water, it's gonna sizzle, it's gonna spark, and I'm gonna demo that one day. It's gonna sizzle, it's gonna spark, it might even catch on fire. If I took the same amount of francium and threw it in there, it's probably going to pop and splatter water all over the room, if not break the glass that it's in. All All right. So when we talk about so one physical property that's kind of sometimes it's physical, sometimes it's chemical, is odor. So like gasoline, you pour out some gasoline or you go to the gas station, you can smell the gasoline. That's physical property of it. But if you think about like an orange, if you leave an orange sitting on your counter for a long time, does the orange smell the same the whole time it's there? All right. So when you think about that odor of it changing over time, that's more of a chemical process. But if it's just what does an orange smell like, that's physical. What does an orange smell like as it's rotting is chemical. All right. So, and then flammability is more of a chemical property that we look at, and we can really only know flammability when we test the flammability. All right. We know that gasoline is flammable because we've seen it burn over and over and over again. But if you have a new substance that you're not necessarily familiar with, you're going to have to test to see if it's flammable or not. All right. All right. So, can everybody see this? All right. So real quick in your notes, I want you to list 3 physical properties of this. All right. So what are some ways that we could describe that?
It's blue.
All right. We can describe it by its color.
It does have an odor.
Well, we don't know that because I have it closed. So, all right. We can describe
It's a container.
it's a liquid. All right. We can describe it as being blue. We can describe it as being liquid. Now the rest of them. So if I hold it up to a light, does light pass through it? Somewhat. So it's translucent, if not transparent. It's not completely transparent because you can't totally see through it. If it got thick enough, you wouldn't be able to see through it. So we could call it translucent, or light can pass through it. We could potentially measure the volume of it. We could measure the mass of it. We could measure the density of it. All of those things would be physical properties of it. The fact that we could even call this, aside from the dirt that was at the bottom of the container when I poured this in there, it would be a homogeneous solution. All right, it would be homogeneous. All right. Right now it's kind of heterogeneous because I have some dirt or some other kind of reaction that happened when I poured it in there and produced some white stuff in there. All right. But we can all describe those. Now, chemical side of it, I don't really know if it's flammable or not. I have a suspicion because I know it's mostly water that it's not flammable. All right. But some things that I could test about it is I could drop a piece of metal in there and I could see if this is corrosive. I could pour a little bit out and I could try to burn it and see if it burns. Those would all be examples of chemical things I can test with this. I could mix it with another compound or another solution and I can see if it reacts or not, to see if it's reactive. So I'm just trying to distinguish physical from chemical. These things, no matter how many times I test that it's blue, it's going to stay what it is. No matter how many times that I verify that it's a liquid, it's going to stay the same substance. All right. But if I start trying to burn it or anything like that, or mixing it with other things, it stops being what it is, then that's chemical. All right. So let me see where I want to go from here. All right. Now, so those are properties. Now we're going to talk about changes. So a physical change is a way that we can change the matter, but not its composition. So what could I do to this that will physically change it, but not change what it is?
Add food color.
Say again? Put it in a different container. I can change the shape of it by pouring it in a different container. All right. I want to avoid adding things to it because it might react. What would happen to this if I stuck it in the freezer? Or what would you speculate that it would happen? All right, it might freeze, so it could go from a liquid to a solid. If I heat it up, what would happen to it? Probably become a gas. So phase change, changing shape, changing volume, all of those things are physical changes. If I pour a little bit out, I've changed the volume, but I haven't changed what it is. So water, and then if we look at just water, water as a solid is still H2O. Water as a liquid is still H2O. Water as a gas or steam is still H2O. All right, so those are all physical. Chemical change. Chemical change. The matter does change its composition. So let me see if I can do this. I don't know if I'm going to get a chemical change or not, but I'm going to try. All right. So this substance is sodium hydroxide. So sodium hydroxide is a clear liquid. It looks just like water. But if I take sodium hydroxide and I pour a little bit of this in there, notice what it did to it.
This is a lava lamp.
It looks like a gel. All right. So I poured it in there. Would you say that that is a physical change or a chemical change? Chemical. It's no longer the same substance in there. It might still have some copper in it or whatever turned it into that blue color, but it is definitely not the same substance anymore. All right. It kind of looked like a gel at first, but now as it kind of settles, it's actually a solid, like crystals or whatever. So we have separated it out, and it's become something else. All right. And so chemical change is the actual act of it. Chemical change would be like, so a chemical property is flammability. A chemical change would be if it's burning. All right. So chemical change is going to be things like cooking, rusting, burning, reacting, all of those things. All right. So a physical change results in a different form of the same substance. If I take a piece of paper and tear it, it's still paper, it's just changed shapes. If I take a piece of paper and burn it, is it paper anymore? No, it's carbon ash and gas that's escaped and water vapor that's escaped and all, whatever the fumes that are produced from the glue in it and all of that. All right, so again, we have to look at what has actually happened there. I'm trying to decide. All right. So I'm just going to write down a couple of things. So physical change, examples of physical change would be like cutting, bending, folding, phase change. All right. Chemical change is going to be things like burning, all right. And so in general, that's what we're kind of looking at. Rotting. Cooking. So think about things for a physical change as things you can do to it and you can still get it back to what it was, versus chemical change. When we do it, it's no longer what it was anymore. It's a completely new substance. That one kind of surprised me. I knew it was going to make a solid, but I didn't know it was going to do that. That might be a part for a new lab. All right. So one more little checkpoint question, and that's it for the notes. So let's look at these statements, and we're either going to classify them as physical or chemical. All of these are going to be changes, but we're classifying it as physical or chemical. So the rusting of iron. Chemical. Evaporation of fingernail polish remover. Physical. It evaporates. It's still acetone, but it's just no longer a liquid. It's a gas. All right. Burning of coal. Chemical. Carpet fading because of sunlight exposure. I would probably lean to chemical on that one. So that one would be like a light interaction. So like photosynthesis is a chemical process. So I would treat it in a similar vein. So like you have something's happening to that dye in the carpet when the sun interacts with it, that it changes color or loses its color. So think about like film developing. Actually, y'all are all digital people. Back in the olden days, when we still use stone carts, we used to take pictures and have to get them developed, and they would use a chemical process to convert the images on the film to colors on the paper. All right, so that's kind of where we'll leave it for today. If you look into chapter 3, active, this is probably like the first 15 or 20 questions in there. But it's all going to be kind of general concept of what we've talked about, element versus compound, pure versus mixture, those kind of things. Once you get into the conservation of mass stuff and all of that, I would actually wait until tomorrow's notes for that. I'm going to point that out in just a minute.